Okay, we are back, and let's look at methane CH4. We will not go through all of the nasty math or adding the orbitals, subtracting the orbitals. I just want you to know how that occurs. We're just going to end up with just give the results of all those adding and subtractings. All right, so methane CH4. Note we have 4 hydrogens. Each hydrogen has a 1s orbital, each with 1 electron in it. The spherical 1s orbital with a hydrogen, 1 electron in each. Therefore, valence bond theory says we need 4 carbon orbitals, each with 1 electron, because I need to overlap the 1 electron in the hydrogen s orbital with one of the orbitals in that with one of the orbitals in the carbon atom that has 1 electron in it to make the 2 electrons in the bond. But when we look at the carbon atom, we see its electron configuration, 1s2, 2s2, 2p2. The valence shell is n equals 2, so we've got the 2s and the 2p, and when we add our electrons in there, we find 2 electrons in the 2s, 2 in the 2p like that. We do not have 4 single electrons in order to overlap with my 4 hydrogen single electrons. So what we're going to do is, okay, how do we get 4 single electrons? What if we hybridize the 2s and all 3 of the 2p's? Do just what we did up above with that s and the p, only do it with all the p's and the s at the same time. Add all of them together, subtract all of them, and do various linear combinations of adding and subtracting these orbitals. And when we do that, what we find is we end up with 4 orbitals at the exact same energy. And since we hybridize the s and all 3 of the p's, we call them sp3 hybrid orbitals. And note, we started with 4 orbitals, the s and the 3 p's. So we end up with our 4, 1, 2, 3, 4, sp3 hybrid orbitals. Just as before, they are all at the same energy, and since this carbon had 1, 2, 3, 4 electrons in it, we put our 4 electrons, 1 in each orbital. Now we can see that this carbon atom, after we've hybridized the s and those p orbitals together, this carbon atom has 4 orbitals, each with 1 electron in them. So now each orbital can bond with the 1s orbital with its 1 electron of the hydrogen to make 2 electrons in that bond. When you look at the shape by doing all those calculations, you find that the shape of these sp3 hybrid orbitals, all 4 of them together, give us this tetrahedral shape, where here is one of our sp3 hybrid orbitals, here's the second, here is the third, and going back is the fourth, and we have a 109.5 degree angle right there. Something very important to note, when you're trying to figure out hybridization and all of that, you look at the geometry first. What is the electronic geometry of your molecule? Once you know the electronic geometry of it, that then tells you what the hybridization must be. If your electronic geometry is tetrahedral, that tells you that the hybridization must be sp3. Because that's the only way to get a tetrahedral geometry with these orbitals that are not normally 109.5 degrees apart. They're normally 90 degrees apart. The only way to get 109.5, a tetrahedral shape, is with sp3 hybridization. So the shape comes first, then once you see the shape, then you know the hybridization. Okay. So let's look at the next shape. Let's look at the trigonal planar geometry. All right. So how do we get trigonal planar? How do we hybridize things to get a trigonal planar geometry? It turns out, by doing all the math and everything, that if you, say, have a carbon atom and you hybridize the s and 2 of the p's, don't hybridize that third p orbital. Just hybridize the s orbital with 2 of these p orbitals, and you end up with sp2 hybrid orbitals, 3 of them. Yes, 3 orbitals, 1 s and two p's together make three sp2 hybridized orbitals that are all at the same energy, and we have the unhybridized p. We move our four electrons, one in each orbital and one in unhybridized p, and that will give us an sp2 hybridized atom. Note, you saw that the atom was trigonal planar. VSEPR theory told us it was trigonal planar. And because it's trigonal planar, we now know it must be sp2 hybridized, that central atom. Okay. And so if we're actually to draw it, if here's the nucleus of our molecule, we have our unhybridized p orbital going straight up and down like this. And a little tough to see on a two-dimensional sheet, but here's one sp2 hybrid going this way. This sp2 hybrid is kind of coming out at us in the trigonal plane, and back here, tucked back there, is the other sp2 hybrid orbital going backwards and to the left. So let's look at this molecule here, H2C double bond CH2. Here's the Lewis structure for it. And if you're doing VSEPR theory, note we have two central atoms at this point. Here's a central atom and here's a central atom. So let's look at them one at a time. Let's look at this carbon as the central atom. And note there are 1, 2, 3 electron groups coming off of it. How do 3 electron groups get maximum angle apart? That's right, 120 degrees, trigonal planar. So we know this carbon is trigonal planar, which tells us it now tells us it is sp2 hybridized. Note this carbon, it's the same. 1, 2, 3 electron groups coming off of it. Recall the VSEPR theory treats double bonds as just one electron group. 3 electron groups coming off of it, also sp2 hybridized. And which means this is trigonal planar and this is trigonal planar, and it turns out if you were to actually rotate this molecule 90 degrees, you would find out that this trigonal plane here is coplanar with this trigonal plane. This molecule is completely flat. Rotate it 90 degrees and you see the carbon-carbon double bond is here. This hydrogen is sticking out, this one's sticking out, that one's going back, that one's going back. You do not have the case where this would be coming out, that would be going back, this one coming up this way and one down that way. That doesn't happen. This molecule is always flat. Well, why is that? And how do we get that double bond? Well, let's take a look. I've already drawn our first carbon here. Here's this carbon with its unhybridized p going up and down. And here's this sp2 hybrid going this way with its one electron. The sp2 hybrid this way with its an electron. The other sp2 hybrid tucked back there with its one electron. And yes, the unhybridized p has its one electron. We already noted that this other carbon is also sp2 hybridized, so it will look the same as this one. So when we draw it, here's the carbon nucleus. We can draw the sp2 hybrid overlapping that one, and it's got its unpaired electron. We've got the sp2 hybrid going back this way with its unpaired electron. That one's actually coming out towards us. Here's the one tucked behind it going back. It's got its one electron. And we also have the unhybridized p orbital, like this, with its one electron. And before we get into the real meat and bones of that double bond, let's put in our hydrogens. Each carbon has 2 hydrogens on it. So we've got a hydrogen up here and a hydrogen back here. And each of those hydrogens has 1 electron, so we are forming the bonding pairs here and here. We've got a hydrogen here and a hydrogen there. So we've got overlapping properly. We've got their bonding pairs, so there's those 2 single bonds. And now we get to the double bond. Recall, one of the ways that orbitals can overlap to give bonds is these p orbitals overlapping side to side like this. So it turns out that these 2 p orbitals are actually overlapping each other, as you know we can get from various bonding orbital geometries. And so that forms our pi bond. Note that this carbon-carbon bond here is a sigma bond. So you have this sigma bond as these two sp2 hybrids are overlapping each other. Our sigma bond here. We've got the hydrogen 1s overlapping with the carbon sp2 hybrid is another sigma bond here, here, and here. But this unhybridized p orbital overlapping with us unhybridized p, notice this orbital overlapping with this orbital, also is a bond. That is a pi bond. So what that tells us is our double bond is actually a combination of a sigma bond and a pi bond. Also note, double bonds are stronger than single bonds, but double bonds are not twice as strong. The reason is because this sigma bonding interaction is stronger than this pi bonding interaction. The fact that even to show these two overlapping, we had to draw these little swooshes to indicate, okay, yeah, those two are overlapping each other, tells us that this pi interaction is probably going to be not as strong as this sigma interaction. And it is not. Okay. Note, as we said before, our sigma bonds versus pi bonds. If we didn't have this pi bond here, you could have rotated this carbon, held this one still and rotated this one along that bonding axis like this, and you would not have changed this overlap here. But note, if you've got pi bonds, if you held this bond vertical like this unhybridized p orbital, but rotated this carbon so that this bond was kind of spinning around like that, note that when you spun it 90 degrees, there's no overlap anymore, which means this pi bond cannot rotate because it changes the overlap. Changing the overlap means you have to break the bond, and breaking the bond takes a lot more energy. So pi bonds do not rotate, which means when you have this carbon-carbon double bond here, you've got the sigma bond and the pi bond. The fact there's a pi bond means that these two hydrogens cannot be rotating around. These two will always be in the same plane as these two over here. And the last thing to note about this double bond is something you're probably looking at this and saying, are you crazy? I can see that these two are overlapping just fine, but you're trying to tell me that these two are actually, that this lobe is actually overlapping with that lobe and this here? It's like, yeah, I am telling you that happens. The deal is I cannot draw that properly and have you see it nicely. Oh, you can't, you say? Well, okay, fine, I'll do it. Here's the thing. When we draw these orbitals, we draw what we call skinny orbitals. I don't think that's the scientific term for them, but that's what we call them, skinny orbitals. Those are not how the orbitals actually look. P orbitals don't actually look exactly like this. sp2, sp3 hybrids don't actually look like that. It turns out if we want to draw real orbitals, it would look like this. If we had this carbon here and this carbon here representing these two carbons up here, if I want to draw this sp2 hybrid orbital, it actually looks more like this. And so the other one on this carbon looks like this. Okay, nice. What do the unhybridized P's look like? If you're actually looking at the unhybridized P's, they look like this. I didn't even draw these right. These need to be bigger because they're actually you'd see there'd be overlapping each other right here. But note, look at our other sp2 hybridized orbitals. I had to draw the one coming out this way and the one behind it, and the one coming out this way and the one behind it. Now I've got to put in my hydrogen 1s orbitals there and there and there and there. And what does that look like to you? Yeah, it kind of looks like a big old blob, and truthfully, that's what molecules look like. They kind of look like big old blobs. Yeah, but note, very difficult to actually see what's going on if you draw the orbitals in their actual shape, what they really look like. So we draw these skinny orbitals. And when you draw the skinny orbitals, it is much easier to see what is overlapping with what. The downside, the problem with drawing skinny orbitals, is anytime you have a pi interaction, you have to do this type of business. You have to put, oh, yeah, this is this and that's there, because you have to indicate that they are overlapping each other, because they are. It's just in order to show it, you'd have to draw something like this. All right. Now, if you don't like my drawings, and lots of people don't, you can go to the book. The book has a pretty good, nice, colorful representation of what's going on with these orbitals. Here you've got the hybridization, where you had the 2s and the 2p's, and then their electrons, and then here's our 4 hybrid orbitals, sp3 hybrid orbitals we get out of it, and we tend to draw it like this. They've got nice diagrams of the s orbitals and the p orbitals, and then when they overlap, here's our hybrid orbitals. This is page 459 in the book, and much better than I can, they have a nice picture of the methane molecule with the carbon in the middle here, and the electrons, and paired up with the hydrogen. So they do a pretty good job of that. And because they do a pretty good job of that, I'm going to just use the book to look at our other hybridization schemes that we have here. All right, before we do that, note, let's look at the Lewis structure. Ooh, nasty. Let's look at ammonia, NH3. Note, if you were to do the Lewis structure of NH3, you would find that you've got the nitrogens, the 3 hydrogens. If you do the Lewis structure, you would find this: nitrogen, hydrogen, 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 lone pair on the nitrogen. The SEPR theory then tells us the electronic geometry is tetrahedral. Note the molecular geometry. If someone asked you what's the shape, you would say the molecular geometry is trigonal pyramidal. But so the molecular geometry, the shape is trigonal pyramidal, but there are 4 electron groups coming off the nitrogen. The electronic geometry is tetrahedral. Therefore, if the electronic geometry is tetrahedral, the hybridization on this nitrogen is sp3 hybridized. So here would be the ammonia molecule sp3 hybridized to give us the trigonal pyramidal shape with the hydrogens, but tetrahedral when you consider the lone pair up there. Very important to remember that hybridization is all about the electronic geometry. All right. We already did that CH2 molecule. Here's how your book represents it. And they did, looks pretty similar to what we did. Looks similar. Note how nasty they have to look. Look how they draw this, how they said, oh, we're overlapping here and we're overlapping here. They have the same problem we did. These are all skinny orbitals, and it doesn't look like there's any overlap happening. If there is, so they represent it with these like tubes going between there. Yeah, you just have to somehow find a way to show using skinny orbitals that they're actually overlapping each other when you look at the actual orbitals themselves. All right. So, cool. There's some more molecules they talk about. Note what happens if you have this molecule right here. I will draw it. Very light. If you have HC triple bond CH, there is our Lewis structure. There is, well, VSEPR theory, what does it say? Well, we've got 2 central atoms here. You can look at this carbon as a central atom and this carbon as a central atom. Note, a single bond, a triple bond. VSEPR theory treats this as 2 electron groups. So if we have 2 electron groups coming off this carbon, it is linear. This hydrogen's on one side, This carbon's on the other side, 180-degree angle. HCC angle is 180 degree. Note, we already covered that. What hybridization gives us 180-degree angles? That's right, sp hybridization. So when we're looking at that molecule, our hybridization will be sp, where we've got the 2s orbital and one of the two p orbitals. We're going to hybridize them to give two sp hybrid orbitals and two unhybridized p orbitals. All right. When you look at how the electrons, what orbitals they go into, note our hydrogen had the 1s, the carbon had the 2 electrons in the 2s, and then here's the 2 p's. After hybridization, we've got the 2 sp hybrids, the 2 unhybridized p, each with 1 electron, and this one's actually going to form 1 sigma bond, the purple sigma bond in the middle here, and then 2 pi bonds. Here's 1 pi bond up here and down here, above and below. Here's a second pi bond, like coming out towards us here and back here. So a triple bond consists of 1 sigma bond and 2 pi bonds. 1 sigma bond from the overlapping sp orbitals on each carbon, and then 2 pi bonds from the overlapping unhybridized p in this direction, and the overlapping unhybridized p's in this direction. So that's how we get a triple bond, 1 sigma, 2 pi bonds. All right. And there are other hybridization patterns when we have our molecules that have more than an octet. Here's ASF5, Trigonal Bi-Pyramidal. What's the hybridization for the shape Trigonal Bi-Pyramidal? Where it turns out, as we've said before, you can get Trigonal Bi-Pyramidal geometry. You can expand the octet if you dip into the d orbitals. And so we're going to actually hybridize a d orbital in here. If you have trigonal bipyramidal geometry, that's going to be sp3d hybridization. If you have octahedral geometry, 6 groups coming off a central atom, that'll be sp3d2 hybridization. All right. So, pretty nice table, table 11.3 in your book here, that just goes through all of these hybridizations. And note, as they indicate here, very important, the electronic geometry, move this up a little bit. Note, it's the electronic geometry from VSEPR theory gives you the shape, and once you know the shape, then you know the hybridization. And also note that we've been looking at atoms, or molecules that have 1 central atom. Today we looked at molecules with 2 central atoms. You can have more than 1 central atom, and you have to look at the hybridization of each central atom in your molecule. All right, well, this sounds good. That's a lot to digest. This video is running a little long, but that looks very interesting. Hey, I wonder if we can add another theory that's even more difficult. I bet you we can. That's coming up next.